Oracle Database Architecture, Comprehensive Lecture Introduction. Good morning, everyone. I'm Mr. Bell from Ctech, CaesarBrotherTech.com, and I'll be your instructor for today's deep dive into Oracle Database Architecture. This is Lesson 16 in our Database Management series, and I'm excited to guide you through this fascinating topic. Today, we're going to explore the intricate workings of Oracle Database, one of the most powerful and widely used database management systems in enterprise environments. Think of an Oracle database as a sophisticated digital library with various components working in harmony to store and manage your data efficiently. Our session today will cover both Part 1 and Part 2 of Oracle Database Architecture. In Part 1, we'll focus on memory management and background processes. In Part 2, we'll examine storage architecture and concurrency control. Let's begin our journey into the world of Oracle. Part 1, Memory Management and Background Processes. Basic memory concepts. Before we dive into Oracle's specific memory structures, let's understand why efficient memory management is crucial for database performance. Speed. Memory access is dramatically faster than disk access. It's like finding a book on your desk versus traveling to a library across town. Sharing. In enterprise environments, hundreds or even thousands of users might need simultaneous access to the same data. Caching. By keeping frequently accessed data in memory, we can significantly improve application performance. To help you visualize Oracle's memory architecture, think of it like a busy restaurant. The kitchen represents shared memory, SGA, where resources are available to everyone. Individual tables represent private memory, PGA, where each customer has their own space. Our system, global area, SGA. The SGA is Oracle's shared memory area, the kitchen in our restaurant analogy. Every user connection to the database shares this space. Let's explore its key components. 1. Database Buffer Cache. The buffer cache is where Oracle keeps recently accessed data blocks to avoid repeated disk reads. Here's how it works. When you first run a query like select from employees, where employee ID occur 100, Oracle must read the data from disk. If you run the same query again, the data is already in the buffer cache, making execution much faster. The buffer cache has 3 main areas. Default pool, for regular data storage like the main kitchen area. Keep pool, for important reference data you want to always maintain in memory. Recycle pool, for temporary data that won't be needed repeatedly. For example, if you have a small lookup table that's frequently accessed, you might place it in the keep pool. SQL alter table country codes, storage buffer pool keep. 42. Shared pool. The shared pool is where Oracle stores SQL statements and execution plans. Think of it as a recipe book that gets reused. When a SQL statement is first executed, Oracle parses it and creates an execution plan. If the same SQL is executed again, Oracle can reuse the existing plan rather than recreating it. This component is crucial for applications that repeatedly execute the same queries. You can check if your SQL statements are being reused with SQL select SQL text executions loads from vSQL where executions, one order by executions, desk. High execution counts with low load counts indicate efficient shared pool usage. 3. Redo log buffer. The redo log buffer is a circular memory buffer that temporarily stores records of database changes before they're written to disk. This is critical for database recovery in case of system failure. Think of it like a restaurant's order pad. All orders are written down before being delivered to ensure nothing is lost if there's an interruption. You can monitor redo activity with SQL. Select name, value from VRC stat where name like redo%, 1GR Squire program global area, PGA. While the SGA is shared memory, the PGA is private memory allocated for each user session, like giving each restaurant customer their own table. Key PGA functions include session, memory, stores user variables and login information, sort areas, handles operations like order by and group by, hash areas, used for operations like hash joins. Let me show you a practical example of monitoring sort operations. SQL, create a test table, create table test, rsort, ID number, data varchar2 SAQ 100. Insert sample data begin for I in, 1000 loop insert into test sort values I dbms random.string a50 end loop end run a sort operation select from test or sort order by data check sort usage select name value from vp guesstat where name like %sort%. D for background processes. Background processes are like the staff in our restaurant analogy, each with a specific job to keep things running smoothly. Let's look at some key processes. Sakuar 1. Database writer, DBWR. The DBWR process writes modified data from the buffer cache to disk. It's responsible for making your changes permanent and freeing up buffer cache space. You can monitor DBWR activity with SQL select name value from via systat where name in physical writes direct physical writes from cache. 2. Log writer, LGWR. The LGWR process writes redo log entries from the redo log buffer to disk. This is crucial for database recovery, ensuring that no committed transactions are lost, even if the system crashes. You can check redo log activity with SQL select group inr sequence er bytes edr tenor24 as size MB members status archived from vlog edr car 3 system monitor SMON. The CMON process performs various system maintenance tasks, crash recovery when the database restarts, cleaning up temporary segments. Coalescing free space in table spaces. Let's take a moment to practice monitoring these components. Please run these queries in your environment and observe the results. SQL, check overall SGA allocation, select from VAS SGA, check shared pool usage, select from VAS SGA stat. Where pool, shared pool, check PGA usage, select from VP Gastat. Share Part 2, Storage Architecture and Concurrency Control, Nashishur with Storage Architecture. Now let's explore how Oracle organizes and stores data. Think of Oracle's storage architecture like organizing a massive library. You assume table spaces are like different sections of the library, fiction, nonfiction, etc. Segments are like individual bookshelves. Extents are like shelves on each bookshelf. Blocks are like individual books. Watcher 1. Table spaces. Table spaces are logical containers for your data that help you organize different types of data and manage them separately. Common types of table spaces include system, for Oracle's own data dictionary, like the library's catalog system. Users, for user data, like the main book collection. Temp, for temporary operations, like a reading room. Undo, for rolling back changes, like a book return area. Let me show you how to create and manage table spaces. SQL, create a new table space. Create table space, user data, data file, user 1, app, Oracle, data, user, data 01, dbf size 100 made auto extend on next 50 made extent management, local segment, space management auto, check table space usage, select table space, name, round used space, 8192, 1024, 1024, 2, as used, MB, round table space size, 8192, 1024, 1024, 2, as total MB, round used space, table space size, 100, 2, as used PCT from DBA table space, usage metrics, measure 2, segments, extents, and blocks. Segments are database objects like tables and indexes, or extents files are groups of continuous blocks allocated to a segment. Blocks are the smallest unit of data storage, like pages in a book. Let's see how to monitor space usage. SQL, create a table, creates a segment, create table sales, data, ID number primary, key, sale, date, amount number, intent 2. Segment, creation immediate table space, user data, check segment space usage, select segment, name, segment, type, table space, name, bytes, 1024 to 1024, as size and B's extents, blocks from DBA segments where segment, name, sales data are full concurrency control. One of the most impressive aspects of Oracle Database is its ability to handle multiple users working with the same data simultaneously. Imagine multiple librarians trying to update the same catalog entry. How do we prevent conflicts? 1. Transaction management. Oracle uses transactions to group a series of operations as a single logical unit of work. This ensures data consistency when multiple users work simultaneously. Let's walk through a practical example. SQL. Session 1, start a transaction, update sales data set amount plus 100 where ID 1. Don't commit yet. Session 2, try to update same record. This will wait for session 1 to finish. Update sales data set amount 50 where ID carries to 1. Check for locks. Select SID, type, L mode, request, block, C time from block, where block, 0. In this scenario, session 2 will wait until session 1 either commits or rolls back its transaction. There 2. Understanding locks. Locks are mechanisms to prevent conflicting changes and ensure data integrity. Oracle uses several types of locks. Row locks. Lock individual rows being updated. Table locks. Lock entire tables for major changes. System locks. Lock internal database structures. You can monitor lock conflicts with SQL. Find sessions waiting for locks. Select S username, SSID, S.serial, S.wait class, S.seconds in wait, S blocking session, SQ. SQL text from vSession, S join, vSQL, SQ on S.SQLID, SQ.SQL ID, where S blocking a session is not null. This query helps you identify which sessions are blocking others and the SQL statements involved. WAS, performance monitoring. Before we conclude, let's briefly touch on performance monitoring. Oracle provides powerful tools to monitor and optimize database performance. 1. AWR, Automatic Workload Repository, collects performance statistics at regular intervals. 2. ADDM, Automatic Database Diagnostic Monitor, analyzes AWR data to identify performance bottlenecks. 3. ASH, Active Session History, samples active sessions to provide detailed workload information. These tools help you identify high-resource SQL statements, contention issues, I/O bottlenecks, memory configuration problems. Summary. Let's recap what we've covered in today's session. Part 1, Memory and Background Processes. SGA is shared memory used by all database users. PGA is private memory for each user session. Background processes work together to maintain database stability. Part 2, Storage and Concurrency. Oracle organizes storage using tablespaces, segments, extents, and blocks. Transaction management and locks enable multiple users to work with the same data safely. Performance monitoring tools help identify and resolve bottlenecks. Understanding these fundamental concepts will provide you with a solid foundation for working with Oracle database in production environments. Practice assignment. To reinforce today's learning, I'd like you to complete the following tasks. 1. Run the monitoring queries we discussed against your Oracle database. 2. Create a test case demonstrating transaction isolation. 3. Document your findings in a brief report. Are there any questions before we wrap up for today? Thank you for your attention, and I look forward to seeing you in our next session where we'll explore Oracle's data security features and backup recovery strategies.